I'll start with the following observation. Fields take off when they find their language, and it's very important for them to find their language. So the question arises, has AI found its language? Well, there have been AI-specific languages going back to the 50s with Lisp, and then in the 70s with Prolog. And they had some really nice features like automated reasoning right out of the box. But they also didn't have other things like learning, for example. And in the end, they were swept away by more general purpose languages. Then in the 90s, graphical models like Bayesian networks emerged as a lingua franca for statistical AI. And again, many nice features, but the inference was not very scalable and they had other issues, so they didn't take off at the end of the day. In the 2000s, things like Markov logic networks combined the more classic AI and the probabilistic AI. And again, you could do a lot of things very elegantly in something like Markov logic, but it also suffers from things like the inference being very expensive. And did not take over in the end. These days, on a practical level, the language of AI is Python, and Python is a wonderful language. But as a language for AI, it's a really strange notion, right? No one would have imagined when it was proposed that people would actually find that a good match. And in fact, what people do is on top of it, they use things like NumPy, PyTorch, TensorFlow, et cetera, JAX. And these are nice, but again, they only have some of the features that you want out of a language of AI. These things run on GPUs, and the learning can be done by gradient descent, again out of the box, and that's all good. But they don't do things like, for example, automated reasoning right out of the box. There's this field of neurosymbolic AI that does try to have these different things, but so far, at least, there is no really one, good language to do this. And so I propose we start with the following question. What do we want the language of AI to do, right? And then try to develop a language that has all those features. Well, first of all, it should have everything that's not AI so that people can focus on what matters. It should allow you to easily incorporate domain knowledge and reason automatically over it, like the classic AI languages, but then it should also learn automatically, like newer libraries can do. And the models that are learned ideally should be transparent. The whole thing should be reliable and should scale effortlessly without you having to do a lot of hacking just to make it scale. So if you look at these things, some of them, like easily incorporating knowledge and reliability and reasoning automatically and transparency, those are characteristics of symbolic AI. Things like learning automatically and scaling effortlessly are characteristics of deep learning. So clearly, we want a language that combines both of those things, and that's exactly what I'm going to describe now, is a new language called Tensor Logic that combines deep learning and symbolic AI by combining the fundamental mathematical languages that they are each based on. In the case of deep learning, tensor algebra, and in the case of symbolic AI, logic programming. So let me start with a whirlwind tour of logic programming and tensor algebra, and then see how we can combine them and what we can do with the combined language. A logic program is a set of rules and facts. A fact says that a relation applies to a series of objects. For example, parent Bob Chris says that Bob is Chris's parent, and ancestor Alice Bob says that Alice is an ancestor of Bob. And a rule says that if the body of the rule then holds, then so does the head. If body, then head. The body is a series of antecedents separated by commas, and the head is also known as the consequent. So, for example, these two rules are the definition of the ancestor relation. X is Y's ancestor if X is Y's parent, or if there's a Y such that X is Y's ancestor, and then Y in turn is Z's parent. And the two main logic programming languages are Prolog. In Prolog, the arguments of relations can be constants, variables, on functions. In Datalog, there are no functions, and we won't need them here because, as you'll see, we'll get them in a different way. So we're going to use mainly the Datalog form of things. And one important thing for what follows, I see that the slide is not displaying completely correctly, but we'll survive, is the database view of logic programming. In database terms, a rule is a series of joins followed by a projection. And as you all know, the join of two relations R and S is the set of all tuples that you can form for tuples in R and S that have the same values of the same arguments. So for example, if you join these two tiny relations here on the screen, on the Y argument, then Alice Bob joins with Bob Chris to form Alice Bob Chris. Then the projection of a relation onto a subset of its arguments is the relation that you obtain by discarding all the arguments of R that are not in G. So for example, if you project Y out, you get, for example, then just the tuple Alice Chris. And as you've probably noticed, what we've actually done here is just apply the second rule that I had on the previous slide to obtain that Alice is an ancestor of Chris via Bob. So that's the representation. How do we do inference? Two main ways. Well, there's three. There's resolution, but we won't be needing it here. In forward chaining, we repeatedly apply all the rules to the facts that are given as input until no new facts can be inferred. In backward chaining, we're given a query. First of all, we check if it's a fact, and if it is, we return that fact, or we return yes. If not, we try to find rules whose head is the query, and then we repeat the process with their bodies. So for example, if you ask the query, is Alice an ancestor of Chris to the tiny database that we saw before with those rules defining ancestor, the answer is true. Or more interestingly, you can ask who are Alice's ancestors, who is Alice an ancestor of, by typing ancestor Alex X ? And then the answer is Bob and Chris. So that's logic programming in a nutshell. Now for tensor algebra. Neural networks are essentially all programmed using tensor algebra and then univariate nonlinearities, right? With those two things, you can do practically everything. Univariate nonlinearities are simple. What is tensor algebra? Well, first of all, in computer science, as you know, a tensor is defined by its type, which could be real, integer, Boolean, etc., and its shape, which is the number of indices and the number of elements along each index. So a tensor is a generalization of a vector or a matrix. A scalar is a tensor of dimension 1. A matrix of dimension, a scalar is a tensor of dimension 0. A vector of dimension 1. A matrix of dimension 2. The number of indices or dimension is also called the rank. And the other element of the shape is the number of elements along each index. Okay. The formulas are not displaying, which will make this slightly more interesting. So the sum of two tensors. So the two main operations in tensor algebra or two operations that it can be composed largely out of are tensor sum, where you take two tensors of the same shape and add the corresponding elements, and the tensor product, where you take tensors of any shape and form a tensor with one element for each pair of elements from one tensor to the other that is their product. Okay, and there are other operations like the element-wise product, where you multiply one element at a time to tensors of the same shape, tensor contraction, widely used in fields like physics and mathematics, and all the classic operations on matrices and vectors are special cases of tensor operations. One very important thing for us is what is called Einstein summation, or einsum for short. All of these operations are special cases of Einstein summation, so it turns out the only operation that you really need to do almost all of tensor algebra is the Einstein summation. So what is einsum? This is something that Einstein invented when he was struggling with general relativity and got tired of doing a lot of summations over indices of tensors. And so the convention that he introduced was, let's just not write down the summation signs. And then what we do is, in our expressions, whenever in one term there's a repeated index, then implicitly we sum over that index. Okay. So for example, in matrix multiplication, we could write it as just AB, but then when we have many indices, and this is a tensor that becomes ambiguous, or we could write sum of AI, aij bjk, but that's a little cumbersome. We can just take out the sum and write aij bjk. Okay. And this, in the case of a matrix, is not a big deal. But once you get to tensors with a lot of indices, it's a real. It really simplifies and makes things, clearer. So neural networks can all be programmed as einsum combined with univariate nonlinearities, sometimes multivariate ones, which are really just syntactic sugar. And einsum is implemented in NumPy, PyTorch, TensorFlow, etc. Although a lot of people don't know about it, but if the only thing you get from this talk is that einsum is great and you should use more of it, that's probably already been worthwhile. So on to tensor logic. How do we combine these two things? Well, so there's two key ideas, each one of which is an answer to a question. And the first key idea is the answer to the question, what is the relation between tensors and relations? Right? If we want to unify the two languages, we have to start by unifying the basic data structures that they use, in this case, tensors and relations. And the answer to this question is, in fact, remarkably simple. A relation is just a compact representation of a sparse Boolean tensor. So, for example, in social networks, people often use a matrix to represent the social network, sometimes called a sociomatrix, where, for example, if Alice and Bob are friends, you have a 1 for, in the indices Alice and Bob, and otherwise you have 0, okay? Now, of course, this is not very efficient, and as the number of indices of the tensor goes up, it becomes more and more inefficient because it's almost all zeros. So instead, you can represent it compactly by a list of the non-zero entries, which in this case here would be Alice Bob, Bob Chris, and Bob Dan, okay? So that's the first key idea. The second key idea is the answer to the question, what is then the relation between rules and einsums, right? So logic programming is made of rules. Tensor algebra is made of einsums, as we saw. So how do the two relate? And again, there's a remarkably simple answer, which, as far as I know, hadn't been noticed before. And the answer is that rules are just einsums over Boolean tensors with the step function as a nonlinearity. So, for example, let's take this simple rule, x is z's aunt if there's a y such that x is y's sister and y is z's parent, right? You're somebody's aunt if you're the sister of one of their parents. This can be represented in Prolog as you see here. But if you think of these relations as Boolean tensors, right, as we just saw before, there's a matrix of who is whose aunt, etc. You can just write this using einsum as a sub xz is step function h of sxy pyz. And see here, the y is the repeated index, so you sum over it, which effectively does the disjunction, right? And you get a 1 in aunt or a if there were ones in the corresponding matrices of sister and parent, okay? And in tensor logic, we just write this in a Prolog-like notation, but with square brackets to denote that we're talking about tensors and not relations. And then around that, we have to put the step function, because when there's more than one path between x and y, you will have a number bigger than 1. To just make this be Boolean again, we run that through a step function. So here is tensor logic in one slide, and unfortunately the two defining equations of tensor logic are not showing up, but we can just visualize them. So the two key operations in tensor logic are tensor projection and tensor join. And the tensor projection is a generalization of database projection, and tensor join is a generalization of database join. So what is the projection of a tensor onto a subset of its indices? It's the sum for each set of elements that have one, let's call alpha the set of indices that we're projecting onto. For each set of elements with one value of alpha, we sum them, okay? So we just sum all the elements that have the same value of the indices that we're projecting on, okay? And this in particular, for example, will let us project, a vector can be projected onto a scalar by summing its elements. A matrix can be projected, onto a vector by summing each of the columns. summing each of the columns like this. A three-dimensional tensor, you can project it onto a matrix, and then the matrix onto vectors, and then vectors onto scalars. For example, a cube onto the faces, and then the edges, and then the corners. And so in this way, we can already do a lot of things that we want with tensors. And as I mentioned, if the tensors are Boolean, this literally reduces to database join. A tensor join is a generalization of database join, and what we do here is we have, think of three sets of indices, alpha, beta, and gamma, which would have been on that equation there. And what we do is we take two tensors, and for every value of the common indices beta, we multiply the corresponding values. Okay, if this common set of indices is all the indices, this just becomes the element-wise product. If they have nothing in common, then it just becomes a tensor product. But then you also have all these things in between. And again, in the special case that the tensors are Boolean, then this is just the database join. Okay. And now the sole construct in tensor logic is the tensor equation. A tensor equation is a left-hand side tensor is equal to a nonlinearity applied to a tensor product on the right-hand side. The tensors we just put one after another, like we did in the previous slide. The product, the join is implicit, and that's it. There's some little bits of syntactic sugar that we can introduce to make life easy, as we'll see a couple of examples of later. But essentially, a tensor logic program is nothing but a set of tensor equations. There's no other constructs. Tensor elements are 0 by default. Equations with the same left-hand side are implicitly summed. And tensor types and shapes may be declared or inferred. These things are both useful in their own right, and they preserve the correspondence with logic programming. So here's a couple of simple examples just to ground things out before we continue. Here's how you would implement a one-layer perceptron in tensor logic. It's just one line. It's the equation y is equal to step function of wy xi, right? So y is repeated, so it's implicitly summed over. So what this is doing is the dot product of the two, and then you're passing it through a step function. And then you can declare a vector of weights, and you can declare a vector of inputs, or you could read them from files, obviously. The vector of inputs, instead of being listed in Boolean form, you can just give it as a relation. So for example, in this case, x of 1 and x of 2. And then you ask y question, y question mark, to ask what the value of y isn't, and y is computed. As a slightly less trivial example, here's a multi-layer perceptron, and here's where you start seeing the value of tensor logic as a language to very elegantly encode potentially very complicated neural networks. A multi-layer perceptron is still just one equation, except that now you have, instead of y, you have two indices. Let's say that x ranges over x is the neurons in our network, y ranges over layers, and j ranges over elements of that layer. And now what we do is, you can probably work this out if you sit down for a second with this. To compute layer I, you go to layer x, you go to layer I minus 1, right? And then what you do is, at that point, you're just doing a matrix product. So jk and k will give you j, right? This is a multi-layer perceptron. Slightly more complicated example, an RNN, a recurrent neural network. We now have two indices, x and t. Notice I have this little piece of syntactic trick here where I allow t plus 1 instead of just t. And now what I have is, let's say, a sigmoid function applied to a matrix times the previous state, xjt, plus another matrix applied to the input u. Okay? So this is the representation. How do we do inference in tensor logic? Well, as in logic programming, we can do either forward chaining or backward chaining. We can do forward chaining or as in Datalog, or in RITI, which is like the classic, very scalable algorithm for doing inference in symbolic AI. In forward chaining, we just treat the program as linear code, and we execute the equations sequentially. At each step, we compute the tensor elements whose inputs are available. They may not all be available, right off the bat. And then we repeat this until no new elements can be computed, and then we return the results, right, which contain all the answers to the questions you might ask. In backward chaining, which is what is used in Prolog, which is similar here to what is used in Prolog, we treat each tensor equation as a function, and so what we do is the query is the top level call, and then each equation is essentially a mini program that computes the left hand side by recursing into the tensors on the right hand side and their definitions, and we do this until the query is answered. Okay. And the best choice between these two depends on the application, and you can do either one. In the examples that I'll be using implicitly, what is being used is forward chaining. So how do we learn? Again, there's unfortunately some missing equations here, but one of the nice things about tensor logic is that we can learn everything, even symbolic structures, by gradient descent. And the gradient descent is actually very simple. Because there's only one construct in tensor logic, the tensor equation, all that we have to do is, all we have to know how to do is how to differentiate tensor equations. And that is actually very simple because of the following fact. Think of, for example, the equation y equals ax, right? What is the derivative of y with respect to a? It's just x, right? And now think of y is the dot product, wi xi, right? Now the derivative of y with respect to wi is xi. And now if you now do this for a matrix, right? The derivative of y with respect to an element of the matrix is going to be the summation of the elements of x that it multiplies, right? So in tensor logic notation, the derivative of y with respect to m is just x. And this actually generalizes to tensors of any dimension. So if I have a tensor equation with a tensor on the left-hand side, its derivative with respect to a tensor on the right-hand side is just the product of the other tensors. So all you have to do is get rid of the tensor that you're differentiating with respect to. And as you can check easily, the tensors, the indices all still work out, okay? So what happens as a result is that the gradient of a tensor logic program is just another tensor logic program. And what this is going to have equations, right, for each for each tensor that appears on the right-hand side of some tensor equation. We're going to have the derivative of the loss with respect to it. And in this, slightly simplified notation that I have here, the derivative of the loss with respect to a tensor element is going to be the sum over all the right-hand sides that tensor appears in, of the derivative of the loss with respect to the left-hand side, right? This takes care of the rest of the program until you get to that equation, times the derivative of the left-hand side with respect to the right-hand side. This is just the derivative of the nonlinearity at each, at the point corresponding to that element, times the product of all the tensors on the right-hand side, other than the one that we're differentiating with respect to. And that's it, right? And another advantage of this, so this simplicity is nice because it makes the whole thing very perspicuous and simple to think about, but also very importantly, it makes it easy to scale things up because it maps onto GPUs very well, and all you have to do is scale the heck out of this one operation, and then the whole learning skills as well. So once we have computed the gradients, what do we do with them? We do something called backpropagation through structure. And backpropagation through structure is a generalization of the backpropagation through time that we use in RNNs to any structure, okay? So it allows you to do backpropagation over networks that do not have a fixed architecture, right? In traditional neural networks, it's always the same architecture. Now the architecture could vary for a particular example because I might be using different rules on the example with different facts and so on. But the backprop still works as long as I know the derivatives that come from each of these examples, how to add them up to the for the corresponding parameters, and we do. So here's a couple more examples to make things concrete. Here's how you implement a convnet in Tensor Logic. Two types of layers, convolutional and sum pooling. A convolutional layer, you just say, so you have features, right? With two indices x and y, which are the indices of say the pixels in the image to begin with. And what did you have, for example, a ReLU applied to a filter tensor joint with the image. The filter has three indices, x, y, and the channel. And then the image, for each of those filters, using the same syntactic tree as before, you add the offset dx to the x dimension and dy to I to do the convolution. And then to do the sum pooling, right? Because we're implicitly summing here, and there's syntactic sugars for doing max instead of sum and so on, if that's what you'd like. Is again very simple, right? You just have on the left hand side, you divide the indices by the stride, right? And notice that I've used this. I used two separate equations here for clarity, but you could just combine these two equations into one by literally having pooled on the left hand side, and then the right hand side of the convolutional layer equation. So you can define in Tensor Logic, you can define a whole convnet essentially in just one equation, and you can also define a whole transformer in just a dozen equations. So here's a transformer in one slide. I'm of course not going to go over all of this, but you can probably at this point imagine how this would go, right? Like we have the input, an embedding is just a matrix multiplication. Positional encoding is an equation or two. We add them to form the residual stream, and then an attention layer is three matrix multiplications, right, to define the queries, values, and keys, right? And if you look at the left hand sides of the equations here, this is what they have, right? They have the indices of the matrices, and then an index that ranges over blocks, and then an index that ranges over heads. So the whole attention layer, or like the whole all of the attention layers of the transformer are in just these three equations here. And then you merge and do layer norm, which again are two simple tensor equations. MLP layers we already know how to do, and then you do and then the output is another straightforward tensor equation. So this I would submit is a lot simpler, clearer, and easier to debug and play with and generate automatically, as the case may be, than with languages that we had before. So that's how to do some examples of neural networks in Tensor Logic. How do we do symbolic AI? After all, that's one of the main goals, is to be able to combine the two. Well, the answer is very simple. You just write it in Prolog. Since Tensor Logic is a straightforward generalization of logic programming, whatever logic program you had, you can just now import into Tensor Logic, and it will accept it as is. But now, of course, you can combine things in a much more deeper way than you could before, than just by having like some symbolic routines here, calling some neural networks over there, and so on. And beyond this, you can also very easily and elegantly implement things like graphical models and kernel machines. And even beyond that, perhaps the most exciting thing about Tensor Logic is that now we can do things that we couldn't even think of doing before. Like, for example, we can do reasoning in embedding space that is both sound and transparent, which without Tensor Logic, as you know, is a bit of a challenge. So to summarize, what I have described here is one language for all of AI. Just like in the Lord of the Rings, there's one ring to unite them all. That language is Tensor Logic. And the Tensor Logic program is just a set of tensor equations. And you can view a tensor equation as a numeric generalization of a data log rule, or equivalently as just an elegant way to encode a 9-sum. Much more elegant, by the way, than the very clunky way that it's encoded in things like PyTorch and so on. And one of the nice things about Tensor Logic is that it gives you both reasoning and learning out of the box. You don't have to implement any of those things. You can just worry about building your model on top of them, and maybe tweak them and do variations as needed. And with this, you can get in neural networks that you design that have the learnability and scalability of things like PyTorch, but also these can be transparent and reliable as we have in symbolic AI. So don't leave home without it. To learn more about TensorLogic, go to tensorlogic.org or scan the barcode on your screen. Thank you very much.